All right, now we got everything starting to record. That part's good. So here we go. Okay, that wasn't me. I had my cell phone with me this morning because my daughter should be having a baby any day now. So, and I talked to her at lunchtime, so, and she was spacey, which is entertaining. All right, so under engineering physics, I've posted up here in the announcements, at least on the Tonkawa site, where the science tutors are. Today, the science tutor will be, it's Peyton Malcolm. He's over there. He'll be in the Cultural Engagement Center. You also can go to Kristen Phelps. Kristen Phelps is one of the math tutors, and so you need to go to the math tutor hours to find that. And then there's some other ones that are around on other times, but I did post that there. Under material and assignments, and we are now in week 2. You have a new one. For those of you looking for the week 2 lab, since you have some of you have it today, some of you have it tomorrow. This is the one with the pre-lab questions in it. And there is the week 3 laboratory with the pre-lab questions in it. So everything is there. Maybe. Okay. Not sure what just happened. We're rebooting the computer. All right, yeah. I don't know what's going on. So the week 3 lab is in there in Blackboard. So that's there. I'll go to the document camera for right now. We'll see what happens. Let's try that one for a little bit. See how things go. So the over in in Blackboard in week 2, you've got the lab for week 3, and that one's ready to go, and that's gravity along an inclined plane. It's still one-dimensional motion, but it's gravity along an inclined plane. You will also see that there is a video analysis assignment in there. Now the labs, over here in Tonkawa, I know for sure that the lab computers have the Vernier video analysis software on it. I'm not 100% sure if we have it over on the Enid campus, but there is. So the Vernier system does have some video analysis software. There are multiple apps associated that have video analysis in it. And I've also provided you a link for video analysis. So you should be able to get something that will allow you to do some video analysis. The assignment is going to be, you're going to need to get a clip of one-dimensional motion. And we're going to be talking about one-dimensional motion today. Yeah?
With one-dimensional motion, like the videos that are on the homework, like the cars going back and forth on the...
Yep, that's one-dimensional. Balls being tossed straight up and coming straight back down is one-dimensional. Because
car moving back and forth, is that one?
That car moving back and forth is one-dimensional, but a ball being tossed up and coming straight back down is also one-dimensional. Motion on an inclined plane is also one-dimensional. So as long as it's only moving in one dimension, okay? As long as it's only moving in one dimension. You'll need to get a video, and you're going to try to use video analysis to come up with an equation of motion. And between today and Monday, we should be able, yes, let's restore the pages. Let's see where we're at. It may crash again, who knows. All right, so try this now. Go back to Blackboard, woohoo! There it is, the one-dimensional video analysis. So you're going to get some sort of video of some motion in one dimension, and you're going to have to get the equation of motion for it. Now, under class resources, you will find the link. It says Tracker Software. That is a free software that you can use video tracking. And when I show you how I've done it for the Smiley, hopefully before the end of class today, you'll get a chance to see it. And I have that video assignment due February 1st. So you've got time to play with it, work around it, do some work aspects. Start sign-in sheet for me, man. Thank you. Also there, you've got the link to where you can get your fundamentals exam handbook. So that's, that is a reference that you're allowed to use on exams as well. We'll talk about stuff for exams, but you can use this reference book. You can order the hard copy through the website, but you can also get a free PDF of it. And so it's there. That's where that link is, and the trig reference sheet. And if you don't like your textbook, there's another textbook for you that's in there. So that's all under class resources. So under week 2, we've got one-dimensional. I've got a video on free fall one-dimensional kinematics. There are some helpful problem solutions. One is a pin cast of the mountain problem that we did last week, that where we did the angles and looked at the angles, so that's there. There is also a surveyor problem, and that's another one that may be helpful for you. So I have uploaded those. I've uploaded, and then we'll do the smiley problems and that one. So let's talk about the gumdrops. How many people said there were between 50 and 100 gumdrops? Raise your hand. Okay, so we have 50 to 100. How many said there were more than 100 gumdrops? Raise your hand. Okay, I've got a few that say more than 100. All right. I'm going to tell you there were not more than 100. How many said between 50 and 60? I can't believe there were significantly more than 60 gumdrops. How many said between 60 and 70? Nobody between 60 and 70. How many 70, 80? I got a couple. There's still... Huh? I got a couple in Enid? Okay, cool. All right. So how many says that there were more than 80? How many had 90 or more? Okay. So how many had 91? Nobody? How many had 92? How many had more than 95? Got one that's got more than 95. Do I got anybody that two more than 95? All right. How about 96? Okay. 97? 98? There actually were exactly 100 gumdrops somebody had 100 gumdrops in the bottle. Okay. Exactly 100 gumdrops. And the way to estimate it is you estimate how many gumdrops there are and then use the geometry to get you there. But there are 100 gumdrops. There were 100 gumdrops in my flask. Okay. So that kind of gets us to that spot. 100 gumdrops. All right. This has been a pain in the tissue, so we're going to do it this way, even though it comes up really cool in the video. We're going to do it this way. I'm going to do it with paper. All right. So we're starting chapter 2 now. That's because my office has more than one screen. We're starting with chapter 2, and we're starting with motion. Okay? So that's where we're at. We're going to start with motion. And when we think of motion, we know it's in movement. And now I got it too bright. There we go. We've got movement. And we're actually going to start in one dimension. And when we look at one dimension, I can be doing left to right. I can be doing up and down. I can be doing forward and backwards. But the key is I'm just in one dimension. Now, we can change our dimensions in one dimension a couple of different ways. So if I think of Cartesian coordinates, so those are my Cartesian coordinates. Typically, we think we're traveling along an x coordinate, or we're traveling along a y coordinate if I'm thinking 2 dimensions. Or if I end up in 3 dimensions, I can be going up and down the z-axis. Now, I do use a Latin z. Okay, I use a Latin z and I use a Latin 7. Because if you do like that, you don't know whether that's a check mark, a question mark, or whatever. So when I actually write a Latin 7. So I will put the Latin 7 in there, and I will put the Latin 7 or the Latin cross in the Z as well. That just makes, because is this a 2? Is that a Z? Is that a squiggle? Right? So just so you all know that's actually what I use. I actually use a Latin 7. And there's actually a nice name for it.
Everybody sign this?
Everybody got the signature? Okay, great. So I actually have a Latin 7. So we talk about one-dimensional motion, but now let's look at an inclined plane, which will be the lab for next week. If I have an inclined plane and I have a little cart on my inclined plane, I can turn that inclined plane to have it one dimension. As long as my object is only moving in our one-dimensional framework, that's what we're going to be dealing with. So we're dealing with motion. We're going to start with one dimension. Ultimately, we're going to get to 2 dimensions. And this textbook actually brings in 3 dimensions. But we'll stick primarily with just 2 dimensions, but we'll look at the 3-dimensional one. We can do it. The other part about motion is we have types of motion. And we can think of it, I can have one type of motion that looks like this. I can have a bead going around a circle. I can have a tire rolling, right? I can have a tire rolling. I can have somebody, if I look down on a merry-go-round, and I've got my merry-go-round horses and carts, or my Ferris wheels and carts. These things are moving around the circle. This is referred to as rotational motion. So I have rotational motion. Then if I look at a guitar string or I can have a guitar string and we know we can get it to pluck and go back and forth and have something like this, and we get it moving up and down like that, that's typically referred to as vibrational motion. And lucky for us, we won't see vibrational motion until physics 2, because that's where I start. I start physics 2 in vibrational motion. Okay, so we won't see too much of it, but just know that it's there. But then we have the motion of my car traveling, or my cart, going from point A to point B. And that we usually refer to as translational motion. So I can go translational motion, and I can have combinations of these motions. And one of the places that we can see the combination is down in an inclined plane. So let's look at an inclined plane. Physicists love inclined planes. Okay. If I have a can, or a hoop, or a sphere, it can go down this inclined plane one of 2 ways, right? It can slide down the inclined plane, or I can even just follow the center of mass, right? And I can have it go down the inclined plane. And this is our translational motion. Or I can look at the behavior of a particle that's sitting in the can, and I can have the can roll. And if it's rolling, we know what'll happen is if I'm following that little object, it's probably going to do something that looks more like loop-de-loop if I'm doing it this way. And if I am following this and I'm looking at it as the particle model, I'm looking at the behavior of this little teeny tiny piece that's on my can if my can is rolling. Now my can doesn't have to be rolling, my can can just slide. So that could be a combination of rotational as well as translational motion. So I can have those pieces of motion. So we can look at it. Now, if I'm thinking one dimension, and I'm looking at a number line, so to speak, and we have our car here, our cart, and we start plotting its motion, it could go there, and it could come back, and it could go up, and it could go back, and it could go up. I can look at that travel a couple of different ways. So if this is where I start, and I'm going to give it a position x sub 0 or x sub I, referring to initial position. So that's one of the ways that I can refer to that. Then I can have this end spot as my x sub f, and this is usually my final position. Now my motion has done one of two things. I can look at what we refer to as the change in position, all right, with my delta there, and I can do my change in position. And my change in position is just going to be my final minus my initial. So that's one thing that I can represent. But this, and those of you who've had me for chemistry or you've been in chemistry, this looks like a state function. Doesn't matter how I got from point A to point B, or it doesn't matter the route I took. All that I care about is where I started and where I finished.
We can't see the whole thing.
Can't see the whole thing? Okay.
Is that good? Thank you.
Yeah, so it's my state function. I don't care how I got there. I just look at where I started and where I finished. But we know, because we've looked at it and we've played with it, that the distance traveled is going to be the sum of this whole thing going back and forth, right? So my distance traveled is different than my change in position. Now, it could be the same, but it doesn't have to be. So distance traveled and change in position are two different things. So we're going to have to worry about that. And what we usually end up referring to this is displacement. And this gives me my displacement. And that's looking at my initial versus my final position. Okay, that's just looking at my initial versus final position. So we know we can play with that. Well, one of the things that we do, and this gets us back to sewing back the thing that we purposely broke apart a long time ago, is we can actually represent motion graphically. Right? I can do a time and position plot. All right, so I got position and I have time. So if we're looking at a car or a truck, because I can draw trucks a little better than I can draw cars, and we're going down the road, and we're going down the road at a constant speed, and we've done this oodles and oodles of times, right? We're going down the road at a constant speed. We find our position. We started our position here. A little while later, at a constant speed, we're going up here. A little while later, at a constant speed, we're going up there. And a little while later, we're at a constant speed going right there. And then we stop, okay? We traveled at a constant speed, and then we immediately stop. And now we stay at that position for however length of time. I can plot my position versus time and look at what's happening. Now, my position versus time graph doesn't have to be straight, right? I can do that I'm here, and then I'm down here, and then I'm up here, and then I stay straight for a while, and then I come back down, and then I quickly ramp up, and I do something like this, and I can actually describe the motion by drawing a graph. I can get that motion by drawing a graph. So let's go back and let's look at that graph for a little bit, because we did this in math class, right? And in math class, I have some axis here, and I'm just going to go ahead and say it's time. And I have some axis here, and I'm going to say it's position. I can put a lot of different things in there. And in math class, if I do something and have a nice straight a line here, I get a nice straight line. And we do a best fit line, right? So we can call this a best fit line. Couple of interesting things happen. One, my general equation for a line, we usually write it as y is equal to mx plus b. Where y is my y-axis, x is my x-axis, b is my starting point, and m is my slope. And if I look at my slope, we can look at it as rise over run. So if this is my car or my truck traveling at a constant velocity or speed, we'll talk about the difference here in just a second. And this is one of those places that physics gets a bit confusing, because we're going to use speed and velocity interchangeably, but they're not. Okay, they're not. But if I'm doing that, and I'm traveling along the x-axis, my position is x, this is time, I can now write my equation as x mt plus x naught. My initial starting position, and now I have some sort of slope there. And if I look at that, if I look at the rise over the run, this is a change in x over a change in time. So I get my x final minus my x initial divided by my time final minus my time initial. And this will be in units of, say, meters, and this is in units of seconds. It turns out that this slope is going to be an average velocity or speed, depending on where I'm at. But we've already said this right here is a change in displacement. Okay, so that's a change in displacement. So this, again, goes back to being, from the chemistry perspective, it's a state function. Only cares where I start and where I stop. And I get my time. So my graph becomes very important. And I can use graphical information to describe motion. So I can actually pull back what we traditionally think of in terms of our math. I can use this graph to give me some very, very interesting information. So when you guys are doing your lab, you know, you might get a graph that's a position versus time. And I'm going to give you some data. So my data says that t is equal to 0, 1, 2, 3, 4, 5. I got t is equal to 1, 2, 3, 4, 5. I started at 10.1 feet. And this is in seconds. And then after 1 second, I'm at 10.6. After 2 seconds, I'm at 11.1. After 3 seconds, I'm at 11.6. After 4 seconds, I'm now at 12, because this is experimental data. And then I'm at 12.6. So if I go ahead and plot this, this is my time, this is my position. I'm going to start somewhere right there. I'm going to go up. 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 And I have one that's a little off, and then I go back up. I draw a best fit line. And I'm going to eyeball that best fit line. I'm not going to do this. We don't do the connect the dot thing. Okay? We don't do the connect the dot thing. That's not what we're doing because we are ultimately going to curve fit our data. So then we can do our rise over our run. So I can do that. And if I do that, I get the slope. And I'm going to use 11.6 minus 10.6 divided by, so I'm going from 11.6, that's 3, 10.6, that's 1, so I got 3 minus 1. I end up with 1 divided by 2, I end up with 0.5, and this is going to be in feet per second. And now I have a velocity, or the magnitude of a velocity, or speed. Now, if it's a straight line, that tells me I'm traveling at a constant velocity. Okay? It tells me I'm traveling at a constant velocity, so I can actually pull that information back together. So let's look at a couple other things about displacement. So far we've talked about position, and this one's just my location. We've talked about displacement, and we've talked about distance traveled. So let's look from a character or an idea that we're going to have. And one thing that we're going to get to in chapter 3 is vectors. Vectors have magnitude and direction. So I'm going to jump ahead just a little bit because I want to show the difference between displacement and distance traveled, besides my little one-dimensional item. So on a map, I've got Oklahoma City. I got Fort Smith, Arkansas. And down here I have Dallas. As the crow flies, this is about 220 miles. This is about 200 miles. And this is about 280 miles. Now, if I want to go from Oklahoma City to Dallas, I can go by this route, that's route 1. I can go by this route, and that's route 2. Okay? So if I do that route, so that's right there. And if we remember our vectors, okay? If we remember our vectors, I can write this as a vector that's 220 in my x direction. Remember, these are going to be I hat, j hat, k hat are all unit vectors, meaning they have a magnitude of 1, and they're in the x, y, and z direction. Now this vector, so this is vector 2, so that's vector 1, not vector 2. It works out to be about a negative 198 in the I direction and a negative 198 in the j direction, for grins and giggles, as the crow flies. So I have a vector that looks like this, and I have a vector that looks like this, and I end up with, if I'm adding, because I can add vectors head to tail, because we can add it geographically, and I end up with an R vector here, which is my resultant vector. And if I do this, I can take vector 1 plus vector 2, and I can add my x directions. So I get my 220 minus 198 in the I direction. And I get, because there's nothing in the j direction over here, I get my 198 in the j direction. And somewhere along the line you saw this in algebra class or trig class, or you've seen it somewhere. It's been a long time. We dust the cobwebs off, right? But we've seen it. And if I do that, I know that the magnitude of this lovely is going to equal the square root, and this works out, just so you know, that works out to 22. So this works out 22 squared plus 198 squared. And if I do that, it gives me something about 199. So that's going to be 199 miles. And this right here becomes the displacement. Okay, that's displacement. Now, total distance traveled by that route was my 220 and 280, so it's 220 plus 280 is equal to 500 miles. You can see that these two things are not equal. So my displacement is not the same as total distance traveled. And that comes into play when I'm trying to do speed or velocity. Okay? I'm trying to do speed or velocity because speed is this thing that we look at total distance divided by the change in time. That's speed. Velocity, and what we're ultimately going to find out is velocity is a vector. It's going to have direction and magnitude. But in one dimension, we can look at it a little differently. In one dimension, we're looking at this as my change in position or my displacement divided by my change in time. Okay? So if I'm writing this out in symbols here, I get velocity, we're going to use V for velocity, is going to equal my change in position divided by my change in time. If I want to write it in the calculus notation, I'm writing it as the derivative of x with respect to time. But we've done speed and velocity calculations all our life, right? I'm traveling in a car going from Tonkawa to Oklahoma City. It takes me 3 hours to get there.
You're going slow.
I'm going slow. I'm going slow. It takes me 3 hours to get there because I'm pulling a horse trailer and it's a snowy day. Right? What's my speed, right? Okay. Or we can do it backwards. I'm traveling at 60 miles an hour and I'm traveling for 3 hours. How far did I go? 180 miles. Wow. I mean, we've been doing these calculations since we were in 3rd grade. The difference here, what you're seeing that's different now is, one, if I'm traveling at 180 miles an hour, for traveling for 3 hours, how far did I go? That's assuming that I'm doing my total distance, right? And it's assuming, right, now 9 times out of 10, velocity, we're looking at that same change in position and those numbers are the same, which is why we end up using the word velocity and speed interchangeably, which is why we end up getting ourselves confused at times. So when you're doing your homework in this chapter, be very, very careful because speed and velocity may or may not be the same thing. The other part about this, so this is where you start learning calculus and why calculus is so fun, right? If I take a graph right? If I take a graph and I look at the incremental here, and we can actually do these incrementals, and we actually talk about those incrementals, this becomes my change in x with respect to the same change in time. This becomes a change in x with the same change in time. What happens with my differentials is I start making these much, much smaller. And if I'm calculating an area under a curve, and I draw rectangles, depending on how I draw my rectangles, the smaller I draw my rectangles, the more accurate my area under the curve becomes. And that's where this little d is coming from. It's the same thing as this delta, but we give it a d as we start getting infinitesimally small. Okay? As we get infinitesimally small. The other thing that the calculus helps us out is when I've got a position versus time graph. So now I have a position versus time graph. And this is probably about where everybody is in calc right now. And my position versus time graph goes like this. We've got an object that's traveling something like this, something weird. Okay? Now if I'm in a car, and this is like having somebody pull out in front of me on Highway 60 or 412, depending on which way I'm going. I have to slow down a little bit, and then I have to speed up, and da-da-da-da-da. And I want to know what we call the instantaneous velocity is. Now I know how to do that in the car. I just look at my speedometer, because that's giving me instantaneous velocity. But if I've got this plot of motion, and I want to know an instantaneous velocity, I go to a point on my graph. I want to know my instantaneous velocity at that point in time. And we know how to do this because we've done it in math class. I draw a nice tangent to the curve, right? Draw a nice tangent to the curve. And then I go, okay, there's my rise over my run. And I can figure what the slope is. And this gives me an instantaneous velocity. Because we've done that in math class. Gave us an instantaneous value. And that's actually, if I look at velocity, if I want to look at velocity instantaneous, that's going to be the limit as time approaches 0 of my change in position over my change in time. So that's what limits are good for. Okay? This is what limits are good for. Graphically, it makes a whole lot of sense. But when you're sitting there doing limit problems in calculus, you're going, please poke my eye out because it's driving me absolutely, totally insane.
They weren't that bad. You just plug X in.
They drove me totally insane.
To be fair, we just started. She had to jump through to get the answer to that. Would be insane.
This drives you insane, okay? But really, when you start looking at the physics and you're going, okay, well, what does this physically mean? Hey, it physically means something. It gives me that slope of the curve at that point, and I can actually go directly back and get a value that actually has physical meaning. And that makes a whole lot of sense. Now, why we do calculus this way, don't ask me, because calculus actually, if you look at it where it makes more sense, because I just did it, I'm looking at areas under the curve, all right? I'm looking at areas under the curve, and really, honestly, in your book, you want to look at figures 2.19 in your book to look at the instantaneous velocity type stuff. And, huh? Yeah. What's the question? You're going to have to come up to the mic because I can't hear you.
Okay, so that point you picked, the rise over run, is that the instantaneous velocity at that single point that you picked using the limits?
Yes.
Okay, just wondering. Thank you.
Yep. Because then we could do it in another place on the graph too. We could do it there. So you can do it in another number of different places. So one of the things is this text actually probably does it better than any other text that I've ever seen, showing the physical aspect of connecting instantaneous velocity in the graphs and showing how the graph, looking at my position versus time graph. So if I'm traveling, so if I have I'm going to do a velocity versus time graph at a constant velocity. So this side is velocity, this side is time. So that is a velocity versus time graph with a constant velocity, right? That's what that's telling me. If I look at the area, so let's say that this is 20 meters per second and this is 5 seconds. If I look at the area under this graph right here, if I look at that area, that is the total distance traveled. Because what we know is if I look at velocity as the change in position with respect to the change in time, then we can play around with this. And I can say velocity times my change in time is equal to my change in distance. And if I look at this area under the curve, I've got my change in distance, my change in position. So this text really does a really good job. And if you want to look at, this one actually is figure 2.21. Looking at how you can relate to areas under the curve to what you have information-wise. And that becomes really important when we want to look at something that looks like this. And this is, I'm now going to plot, this is velocity final, velocity initial, and this is with respect to time down here. I can look at the area under this puppy, and that looks like 1/2 velocity final minus velocity initial times time. I can actually write an equation and get me an average position there. So I can use my graphs to really help me consolidate that information. Okay, I can use those graphs to really help me look at that information. So I'm going to get some equations here. So we've gone through this. We now have velocity is equal to a change in x with respect to time. We can write it out as dx dt. I can do, if I start looking at, now all of this assumes no acceleration. Okay? This assumes that we have no acceleration. But if I drop a ball, we know what happens. Okay? We actually know what happens. And if I do a position versus time graph with something that looks like this, I get something that looks like this. And I can curve fit this. And it looks like something like y is equal to at squared plus bt plus c. If I do a parabolic fit, that's a general equation of the motion. So that's kind of interesting. That's kind of nice and hunky-dory, and you'll actually get that in lab. If you haven't already done it, you'll actually get it in lab. But now if I do a velocity versus time graph, I end up with a straight line. And if I end up with a straight line on a velocity versus time graph, that tells me I have a constant acceleration. So I'll end up with a constant acceleration. I can still rearrange my equations. Okay. So I can have y is equal to mx plus b, except now my y is velocity. My m is going to be whatever my acceleration turns out. My x is t, and that b is whatever my initial velocity was. And it turns out that if I look at my rise over my run, so rise is going to be velocity, which is in meters per second. Run is going to be in seconds. So I end up with meters per second squared. Because remember, I can do this. I got m over s, and I have 1 over s, and I end up with m over s squared. So I can use my unit analysis to help me out. This m then, this m, which is slope, not meters, becomes an acceleration. And if I have the dropping ball, that acceleration ends up being our little g for gravity. Which means if I go over here, I get x is equal to something that's going to be related to gravity, and we're going to show that it's 1/2 gravity, t squared, plus whatever my initial velocity is times time, plus whatever my starting point is. So I can go back off of my graph and just plug it into my equation of motion. And I'm gonna lose Enid, so I can't give you the equations of motion. But I did open up chapter 2 homework. There's chapter 3 pre-work, and we'll start from here on Monday, and there is a quiz for Friday. And the quiz is in WebAssign. Okay? And the quiz should be open now, and it's due by 5 o'clock on Friday, but there is no class on Friday. We're not meeting class on Friday because I will be in Atlanta by now at a meeting.
I have a question before you come on.